the physical approach. And I've lost something here. Okay. So what do we mean when we say physical approach? It means that in vitro we make the actual restoration or implant that we would like to predict the behavior of in the clinical case. And so in here we are actually making a ceramic crown and testing it, not disc shape or bar shaped specimen. And what we will do is we will load that with a higher bite force than we see in the clinical case and measure the distribution of lifetimes until failure. And then we will have another group of specimens that we load at a lower bite force, however, still higher than we see in the clinical case. And this is what we mean when we say accelerated lifetime testing. So higher bite force than the clinical case so that we see failure, we observe failure in a shorter time. We're accelerating the fatigue test. And we fit those data to a regression model so that we can try to extrapolate or forecast to the clinical case what will be not only the average lifetime, but what will be the distribution or spread of lifetimes that we can expect to observe. And those of you who are already familiar with Weibull statistics, I came about a year and a half ago and talked to you about Weibull statistics. And so if some of you were present then or doing research in the area, you will recognize this equation. This equation is the Weibull strength equation, except it's been modified a little bit to account for lifetimes instead of fast fracture strength. The beta up here is the Weibull modulus. Sometimes we use M instead of beta to stand for Weibull modulus. That means the same thing. We have replaced the sigma for stress here with a T for time. So that's the lifetime of the component. And the Greek letter eta here is going to be the characteristic lifetime. That's the time by which 63% of our specimens will fail. And so that's similar to the characteristic strength that we observe in the fast fracture studies. And the PF here is the probability of failure. Knowing these variables, we can calculate the probability of failure at any given time t. And the second equation here has to do with the acceleration. This is the inverse power law. And the inverse power law describes the relationship between lifetime and load level or stress level. And so we have here sigma is the stress level, and eta is the characteristic lifetime for that stress level, and K and N are regression constants that we can fit the data to determine K and N. And so that's how we fit the data to these two equations, and when we combine them together, we get one overall inverse power law Weibull model. And so that's the equation that our software is using. Luckily, we have software to do this for us, so we don't have to do it all by hand. And so why do we want to use the physical approach sometimes? Well, the big advantage is that it doesn't have all those assumptions that we were making about the finite element model giving an accurate stress distribution. However, it has disadvantages of its own. It's very time consuming. Okay? And it requires expensive equipment because you will have to have equipment capable of fatigue testing. So this means having a servo-hydraulic load frame or electromagnetic load frame. And I feel very fortunate. I've inherited a laboratory 4 years ago that has 8 fatigue load frames in it and a bunch of other load frames. So I know I'm very fortunate, but I still try to come up with accelerated ways to test specimens faster. And remember that most laboratories have only one fatigue load frame at their disposal, 1 or 2. And so the time required to test all the specimens can be a real bottleneck in this area of research. And then on top of that, you cannot just run the computer model again for every time you make a change. And so we have to redo the entire test to be certain every time we make any change in the clinical situation. So if we change the thickness of the layers in an all-ceramic specimen, if we apply the load at a different angle, we change one of our materials, change our cooling rate from the furnace if we use a different environment. And you has showed how you make some of those changes of angle or environment, and it entirely changes the behavior, the mode of crack growth. And that's why we can't say that we expect the restoration to behave the same no matter the angle of load application. We have to redo the entire experiment over again. Okay, so it's a very time-consuming method. And there are several things we can do to make it less time-consuming. One of them is planning the stress levels that we're going to assign the individual specimens to be most efficient. And there's been a lot of research over time done on planning this. We have different methods. We used to use this brute force method to find the Volar curve, or the lifetime on the x-axis versus the chewing load or stress amplitude on the y-axis, that type of lifetime prediction. We used to just have to pick levels at random and test lots of specimens at each stress level, and test tremendous hundreds of specimens for each condition. So now we have strategic methods for assigning each specimen to a different stress level to increase our statistical power and test the fewest specimens in the fewest time, the littlest time possible, to get the same predictive results. So we'll look at each of these, the staircase and two-point method, the boundary technique, and the step stress method that we're using in my laboratory now. So many of you are probably familiar with this staircase method or up and down method. It's the most commonly used fatigue method in dental materials over the years. And it was originally designed by statisticians Dixon and Mood to determine the LD50, the lethal dose of insecticide or poison to kill any species of animal, to 50% probability that each animal will be killed by the poison. And it's very good for that. It's not so good for determining the reliability. You have questions? No? Okay. You want to kick me because I'm being too loud? That's your job. And so what do we do in the staircase method is we start off choosing some stress amplitude which is not high enough to cause immediate failure of the restoration. And we have the mechanical load frame do a simulated chewing or cycling at this level. And Professor Lobauer showed us this morning that if we do not fail by 10,000 cycles or a certain number of preset cycles, then we will increase the stress that we subject the next specimen to. And if we do fail before that time, then we will decrease the stress. So the X here means that we have failed before the predetermined number of cycles. And instead of testing a whole group of 40 specimens at this level, we will go ahead and drop down to the next level to test the next specimen. And we have the second specimen does not fail by the predetermined limit, and so we drop down again for the third specimen, and this one survives 10,000 cycles. And so we must test the next specimen at a higher level, and we keep doing this type of walking up and down from specimen to specimen. And the effect is that it focuses most of the specimens just above and just below, very close to the 50% failure load. Okay? And if most of your data is grouped around the 50% failure load, then you will make very accurate predictions about how much time until 50% of your restorations in your patients fail. But how many people want 50% of their restorations to fail in the clinic? No, you don't. We prefer close to 0%, right? And so it turns out that if you use this method and you try to estimate the lifetime for 5% or 1% failures in the clinic, then you cannot make a very accurate prediction with data you gather using this method. And so that convinced Dr. Menig to come up with a new method. He was working in the railroad industry, looking at the fatigue of axles on railway cars. So these axles are under load on the railroad, and they're turning around, and so they're cycling back and forth in fatigue, and they're having a fatigue crack failure. And he said, I would like to have close to 0% failures, and I want to design a new method that will make accurate predictions in that region of the distribution. And he starts off with a similar to the staircase or up and down method of Dixon and Mood, and continues decreasing the load amplitude on subsequent specimens until the first specimen survives. And then he does not step up. He tests half of his remaining specimens at this stress amplitude. And he developed an equation to predict from the percentage that fail before a given time at this stress amplitude where he should jump to test the rest of the specimens to get a good measurement of the 5% probability of failure, the lifetime for 5% probability of failure. And his method was very phenomenological based. He said that in his equation he has a coefficient that should be somewhere between 0.1 and 0.3, depending on the type of material you were testing. And so a few years ago, my postdoc, Dr. Zhang, and I did some Monte Carlo simulations to better define his method. We found his coefficient can be optimum for dental ceramics when it is 0.178. And we found some of the optimal step sizes to give the best results. But then after we have made this method more specific, we became aware through the group in New York University that there is an even better, more efficient method for fatigue testing of dental materials. And that's the one that we are still using today. It's the step stress method of Nelson. Okay? And what Nelson did, and Nelson was a statistician who was working in the microelectronics industry. So he was measuring time until an electronic component fails. How much voltage can you put through an electrical resistor before it burns up over time? And his statistics can also be applied to dental implants and all ceramic restorations. And so what he does is he, in these other methods, every specimen only has one stress amplitude that specimen is subjected to during its entire lifetime. And what Dr. Nelson does differently is he subjects the same specimen to multiple stress amplitudes during its testing. And it may seem at first like that's difficult to get data from that to figure out how much damage occurs at a lower stress amplitude before you subject the specimen to a higher stress amplitude. But he has developed an equation for that, his cumulative damage model, where you figure out at the point in time where you step the specimen up to the next stress level, you figure out how much time has elapsed, and according to the inverse power law, how much damage should have accumulated. And then you calculate the equivalent time to accumulate the same amount of damage. It will be a shorter time at a higher stress level. And then he substitutes the shorter time into the equation here, the equivalent time, and subtracts the time spent at the first stress level from the total testing time to calculate the time spent at the second or higher stress level. And we can step up multiple times as necessary to cause failure of the restoration, and it gets the testing done in a very efficient manner. And to give you an example of how we apply that, we did one study on endodontically treated teeth. We are asking the question, which is better for the lifetime of the reinforcing post, the corona radicular post, to use a fiber, quartz fiber post, or to use a zirconia ceramic post, and which is better to use a single taper design and the geometry of the post, or to have a two-stage post where the diameter of the post does not change very much and then abruptly near the apex has an abrupt decrease in diameter. And so we did a 2x2 factorial study. Our finite element model predicted that there would be, in the case of the zirconia posts, a stress concentration at the interface between the post and the interior of the root canal, which doesn't exist for the quartz fiber post. The quartz fiber post, the highest stress was on the surface of the tooth root.